The other kind, the reflecting telescope, that one we can make them as big as we want. So it doesn't have that issue. So reflecting telescope, these were the first invented by Isaac Newton, 1680. So 1605, maybe about 70, 75 years later, Newton came up with a better model. Notice how many things Newton has done. The law of gravity, all the laws of motion. He basically is one of the inventors, discoverers, or I guess you could say discoverers or inventors of calculus. And he also built a telescope. I mean, so many stuff. So he invented the reflecting telescope. And then this is the basic model of the reflecting. Okay, so Newton says, no, don't use a lens here. Forget lens. Just keep it open. Have the light come in, and then you see here, this one doesn't have a mirror here, but Newton puts a mirror here instead. You see? So nothing up here, mirror down here. So the light comes, and because the mirror is curved, the light goes, and then he has a secondary mirror. So he's just using mirrors instead of lenses. Comes, reflects, hits the secondary mirror, comes. Of course, you still need a lens in the eyepiece. And then you see it. So right off the bat, you see one of the main advantages. You can build this bigger and bigger and bigger and bigger. You see? You can build it bigger, like this. Imagine you build one this big. And then the only difference is the mirror is going to be like this. And then the aperture is going to be much wider. Is the mirror going to sag? Is it going to start sagging? No, because you are actually supporting it from the bottom and the end. You see? You're supporting it from the bottom and at the end. You can keep making them bigger, okay? This one, you can't make them bigger. And see, if you try to make this bigger, boom, boom, you can only support it from this end and this end. You see? Which one? Yeah, this one, you can make it bigger too, maybe like this. But this one doesn't have to be that big, because what's going to happen, if you curve this just right, and actually that's the next topic of the next page, if you curve this just right, the light beam that hits this side is still going to hit that. You can still make it small. Okay? The light that hits here is still going to hit the same spot. The light that hits here, still going to hit the same spot. The light that hits here, still same spot. As long as the curvature of that mirror is correct, you don't have to make the secondary mirror big. Okay? So that gets us to the next slide. The shape that the curvature needs to be is a particular shape called the parabola. Okay? If you don't make it a parabola, you have a problem known as spherical aberration. This is caused if the mirror is not cut perfectly parabolic, and the image will come out blurry. Well, so what will happen if it's not cut parabolic? This one will come and possibly not even hit the mirror. You know, it'll go somewhere like that. This one will come something like that, and it won't even hit the mirror, you see. So if the curvature of this shape is not a perfect parabola, then you have a problem. And the problem is called spherical aberration. Okay? I believe I have a slide here that shows you this problem. So if the mirror is cut kind of spherically, notice the beams of light that hit the edges come and focus here. The beam of light that hits the middle come and focus here. You see? They're not focusing at the same point. So imagine you had your secondary mirror here. So what's going to happen? Well, this one comes, hits, bounces, hits here, and then reflects back. Okay? And then this one comes, hits here, reflects this way, reflects back that way. So you basically having reflections in kind of all over the place. You want every single beam to hit the same spot. So the correction for it, cut the mirror parabola. Now you can put your secondary mirror here. You see? So that goes to your question. You see, now all the beams of light comes, hits same exact spot. Why does the parabola have that property? Well, you learn this when you're taking algebra. An example of a parabola is something like this, y equals x squared. And then every parabola has a focal point, and then a line behind it called the directrix, right? And the definition of the parabola is that this distance minus this distance is always a constant, okay? When you're taking, I think they covered this in intermediate algebra, and on the chapter where you're learning about parabolas, hyperbolas, ellipses, they teach you about the properties of these things. Well, the parabola has a particular point called one focal point. So if a beam of light comes, it's going to reflect, go through the focal point. You see? So the curvature of that mirror, as long as it's a parabola, it has one focal point. Same thing happens with radio telescopes. When you go to that big dish that I was telling you in Barstow, they cut that dish, they make sure it's a parabola, a perfect parabola. You see? And then if they have a receiver, they put the receiver at the focal point of that parabola, and then all the information goes there. You see? So what this one is saying, if you want to fix the issue of a spherical mirror being not parabolic, you either go and grind it again and make it a perfect parabola, or perhaps another way to cure it, maybe a cheaper way, is to put a correcting lens. It has a weird curvature to it, and then it would make it still go have one focal point. So either you make a correcting lens or you grind it parabolic. Okay? The interesting thing is this actually happened historically. The Hubble Space Telescope was sent in early 1900s, early 1990s, around 1993, 94. And the first sets of images that it was sending to us were not as clear as they should have been. So they actually sent the whole team up, and then they grinded it in outer space. They grinded it parabolic. They made sure it was a parabola. Okay, within reflecting telescopes, there are 5 major kinds of reflecting telescopes. There's this one. The light comes, there's a mirror, and it bounces back, and you get inside. You see the person here? Well, of course, that's not going to be on sale in the store. Those are the professional astronomers. They're going to go inside of that one. So you see prime focus, image is formed inside the telescope. You can actually see her. This is one such case. You've got a person inside, and this is the telescope right here. Huge, huge telescope. So he's actually inside of the telescope, analyzing the image, looking at the image. Newtonian telescope, that's going to be this one. The image comes, bounces, and then the secondary mirror is tilted. Okay? So the image comes, bounces, hits the secondary mirror, comes, and then you have a eyepiece right here. And then this is illustrating a very large Newtonian telescope. I believe the one at Griffith Observatory is this one. Yes, I think so. You walk up the stairs, and then you look from the side. You see. This one that's here, Newtonian. Okay? You see here? Nothing is here. Nothing is here. Empty. The light comes. Back here is a curved mirror. Curvature here, you can't really see it from here. Curvature is parabolic. Okay? And then it hits the mirror, it bounces back. Inside here, on the other side, is a tilted mirror. Okay, it's this tilted mirror right here. How is that mirror supported? There's rods on the sides here. See these nuts that are here? They are supporting that mirror. There's 1, 2, 3, 4. They are supporting that the tilted mirror. And then when the light comes, it bounces, it comes out of here. Then I look. Let's see if I can see you guys. Of course, you guys are going to look huge. Okay? Yeah, it's too magnified. So you look up to the top. And then when you're looking at a star, you go altitude, you go up, then you go azimuth. You see? This rotation is the azimuth. You see? And then this is altitude. So if something is in my zenith, I go straight up 90-degree altitude, you see? To view Polaris, what would I do? Look north. What's the altitude of Polaris for LA? 30, 34. So about 34 is about right there. Go like that. Oh, there it is, Polaris. But you got to be outside, okay? This one here, the purpose of this one is it has a cross here, okay? Just so that you can see what you're looking at. So basically the idea is whatever you're seeing at the center of this one, there's a cross. That should be the center of this one. Because sometimes you'll be like, okay, what should I look at? What should I look at? Well, first you look through here. Okay, let me see Polaris. And then you look. And then you look through here. And then you can see it. Okay? So this one is Newtonian. This one, they're usually a little more expensive, I've noticed. Okay, this is Cassegrain. Image is formed at the end of the telescope. So if it was a big telescope, you would put a chair up, then you would come, go, and then basically they would have to have a hole here. So if this was a Cassegrain, this thing here would have been on the bottom. Then I would have to look from the bottom. Or it would be Schmidt-Cassegrain. It would go like that, and then they would still have a tilted mirror, you see? So I wouldn't have to go all the way down to the bottom. So you could basically have this set up down here. It goes up, and then you look from here. That's basically the difference, okay? But when you go online and search the prices, I think I've noticed these ones are usually a little bit cheaper than the Cassegrains. They tend to be more expensive, maybe because of the design or whatever. And then Schmidt-Cassegrain, same as above. So pretty much the same as the Cassegrain. Comes in, reflects. This one doesn't have a tilted mirror, you see. It has a regular mirror. Comes. Here, tilted mirror, goes up, and you see it from the side. Coude or Nasmyth focus, this one, it's not gonna be available for regular purchase. It comes, it goes, and then it goes all the way to a distant spot. Perhaps a room very, very distant where you're analyzing the images. So it's called Coude or Nasmyth, used to focus the light to a remote focal point. So if you're going to buy one, typically the beginner is going to start with a Newtonian. Okay? I would not recommend a refracting telescope, an old one, but they still sell them at Costco or something else. These are the first kind, the one that I said Galileo used. They are refracting telescope. So you see they use a lens here. So there's a lens here, and then there's an eyepiece here, and then you can look through here to see what you're looking at, and then you can look to see the object here. This is first of all, it's bad because the aperture is too small. Even if you get a big aperture, like 3-4 inch, that's still recommended. Reflectings are better, okay? So I think these are kind of gotten out of style now. Want to buy one and then maybe work your way up to a Schmidt Cassegrain. Let's see here. This picture shows us something. It shows us kind of the same idea. Newtonian goes, flat secondary mirror, focal point you see here. So that's that one. And then you got the Cassegrain, comes, reflects, goes through. Nasmyth focus, comes, goes, comes here, goes all the way, remote focal point. So that's probably if you are way over here trying to analyze the image somewhere else. So those ones wouldn't be available for sale. Prime focus also most likely wouldn't be available for sale. It's inside.